So this video is going to be about logarithms and non-linear data. So the first case is when we have something raised to a power when it's a number or a constant term. So in our case, h equals p times m to the power of q, but q is a number. So let's read the question. The resting heart rate h of a mammal measured in beats per minute is modelled by the equation h equals p times m to the power of q, where p and q are constants and m is the mass of the mammal measured in kilograms. Figure 2 illustrates the linear relationship between log h and log m. The line meets the vertical log h axis at 2.25, meaning that's the y-intercept, and the gradient of minus 0.235. Find to three significant figures the value of p and the value of q. So the first thing we ought to do in a question like this, and pay attention, whenever it's log of the y variable and log of the x variable, it will always be this case where the power is a number. So the first thing we ought to do is to take logs of both sides. So we say log h equals log of p times m raised to the power of q. So I can apply the laws of logs here and say log h equals log p plus log of m raised to the power of q. So that's going to be log h equals log p. Now I can bring the q down, so that's q times log m. But remember, I want it in the form of y equals mx plus c, so I'm going to write it as log h is q times log m plus log p. Now, in our question, they've given us the gradient that q is minus 0.235. So that's going to be the gradient. And with this log p is the y-intercept, where it cuts the y-axis. So we could write log h. Now we know the gradient is minus 0.235 log m plus, now log p is where it cuts the y-axis, which is 2.25. So now what we can do, the inverse of a log is called the antilog. So because this is log base 10, we antilog it, so we raise it to the power of 10 on both sides. Now raising to the power of 10 and log will cancel each other, so I'll just get h on its own. 10 raised to the power of minus 0.235 log m plus 2.25. So what we can do here is we could write this as 10 to the power of minus 0.235 log m times, because it's the law of indices, 10 raised to the power of 2.25. So we can also apply the laws of logs again by saying 10 log m raised to the power of minus 0.235 times 10 to the power of 2.25. And we can use our calculator to evaluate these. But before we do that, 10 and raised to the power, and I've got a log, they will cancel, so I'll get m raised to the power of minus 0.235 times 10 to the power of 2.25. So let's use our calculator to work this, what 10 to the power of 2.25 is. Calculator, do 10 to the power of 2.25. That gives me 178 to three significant figures. So it's 178. So if we go back to our equation, it was h equals p m to the power of q. So we can say, in our case, we've got 178 times m raised to the power of minus 0.2 235. Now originally that was P times M to the power of Q. So in our case, we could write that as, well, P is 178 and Q is minus 0.235. And that's both answers correct to 3 significant figures. So the next part of the question states, a particular mammal has a mass of 5 kg and a resting heart rate of 119 beats per minute. Comment on the suitability of the model for this mammal for 3 marks. And with reference to the model, interpret the value of the constant P. So for part B, what we can do, we can say H is 178 times M raised to the power of minus 0.235. So H is 178 times, now the mass is 5 in our case, raised to the power of minus 0.235. So on my calculator I get 121.94 and so on. We can round this up to 122 and we can say this is reasonably accurate. So suitable. So it is suitable. Part C, we can say the following. P would be the resting heart rates in beats per minute of a mammal with a mass of 1 kilogram.